Hello everyone. So, welcome to lecture 38. So, today we will be looking at what is called Landau theory and phase transitions. Now, is it a it looks like this topic so how is it related to something that we have been speaking about so far. So far we have been looking at some statistical mechanics. We said that statistical mechanics actually tells you the microscopic nature of the system. So if there is something like polarization, right, so which is what is called an order parameter, I then say that my system has several states, several polarization domains, or several states in which polarization can exist. So I have all these microstates in my system where polarization can exist. Similarly, if my system has a global strain, there are several micro domains which have local micro strains, right, and the fluctuations in these micro strains or micro polarizations is what relates to your thermodynamic properties, which is susceptibility, or which is the compliance in case of mechanical properties, susceptibility in case of dielectric properties or magnetic properties. Okay. So we were looking statistically that there is something called a partition function which relates statistical mechanics to thermodynamics, that we did, and then we looked at the genesis of some of these properties, okay, so as fluctuations in order parameters. Now we then ask the question, what about electromechanical properties or some sort of coupled properties. Coupled properties will be correlations between two different order parameters. So we sort of vaguely define what an order parameter is. And then we made a note that if the correlations or fluctuations are large between order parameters, that is when or between metrics, then the microstrain micropolarization. So if their correlation is large, that is when the properties are large, the properties enhance, the piezoelectric coefficient for example enhances, right. Then the question then comes, okay, so when can I find these properties to be large, right. So I want to now design materials where the piezoelectric coefficient, my aim of the design is that the piezoelectric coefficient is going to be large. This is a soft material, this is dielectrically soft in the sense my susceptibility is large, this is mechanically soft, let us say, in the sense my compliance is large, or Young's modulus is small, and so on and so forth, right. So so what is a possible design constraint to so to look at such materials, okay. It turns out, like we did in case of PZT, right. So PZT is one of the materials that we looked at. And in PZT we made a comment in passing that near the what is called the morphotropic phase boundary, the properties enhance. That's where more you have a lot of options for the polarization to go in to go to. And so along the mirror plane, we said this has a CM symmetry, right. So along the mirror plane, the polarization can take any orientation along the mirror plane. As a result, if there are fluctuations, this is the configuration that will make sure that the fluctuations are all stable, and you have this energy landscape where you can have several states that jump between each other, right. So the fluctuations are going to be large. And so the both the susceptibility, dielectric susceptibility is large, as well as the piezoelectric coefficients are large. We made that comment, but I want you to observe that this MPP is actually what is called a phase boundary. There is going to be a phase transition between one phase and the other phase, right. So at these, and that phase transition is happening when I change the composition, right. So at MPB I am changing the composition for phase transition to happen, right. Let us say at MPB of PZT, the composition is changed. No, I mean there is a phase transition along the composition axis. There is a phase transition along the composition axis. As we will see in the maybe next class, in the class after. So phase transitions can happen not just by changing composition, they can happen by changing the temperature, they can happen by changing any sort of input, right. So any sort of cause, right. So by changing the electric field, by changing stresses, strains, right. So I can change E, I can change the pressure or pressure, I can change volume, I can change the stress or strain, right. Then I can also change the temperature, right. So, all these variables, right, so upon changing them I can go from one phase to another phase, right. So, I can so phase transitions occur. With all these variables, right. And then what we noted is if I am close, so if I am generalizing by let me generalize the MPB lessons, generalizing the MPB lessons, if I am close to a phase transition, and this phase transition can happen through not just composition, right. So, composition, electric field, pressure, stress, whatever, right. Temperature is also quite important. So if I am close to a phase transition, then the thermodynamic properties, right. So, such as susceptibilities, the D33s or the D, I am going to write D33, but a piezoelectric property, right. Then all the mechanical properties such as compliance, all these things, right, SI, J, KL, all these things enhance, right. I am just going to make this statement now. So, I have seen one data point to make this statement, that is I have an MPB and I will generalize this whatever I studied from MPB to any form of phase transition. This phase transition can happen when I change temperature, when I change electric field, whatever, right. So, it does not need to be just composition. When I change any of these variables, a phase transition can happen, right. So, so if the phase transition is happening, I am saying if I am close enough to this phase transition, then that is one of my design constraints. I need to make my materials always close enough to some sort of it can jump from one state to another state quite easily. So, if I make materials close enough to some kind of phase transitions, then my properties will enhance, right. So, that is a statement I am going to make, and I am going to also show you that is indeed the case. Okay. All right. So, so to understand, since that is my material design constraint, right. So, I will actually look at what a phase transition is, and I will look at theories that actually, simple theories that actually predict where can your material have phase transition, right, and so on and so forth. And one of the simplest theories is what is called Landau theory. Okay. Okay. Now, before going into Landau theory, so let me also one more thing that I did not mention last time, and I was meaning to mention, is if I really go and check out, so okay, in a piezoelectric material, right. So, I said sorry so if I am near the MPB, I enhance the susceptibility, but if I want to increase the reduce the Young's modulus or increase the compliance, right, then in that case I need to use what are called high entropy alloys. So, high entropy alloy, so if I use what are called high entropy alloys, where so this is an emerging field of research in metallurgy, where so people use more than 5 elements and then they mix them proportionately and so on and so forth. All the compositions are here, for example. This is some paper where they have prepared this high entropy alloys at different synthesis temperatures. So, the T here is the different synthesis temperatures. So, they prepared all these high entropy alloys in different proportions, right. So, this tells you the proportion of nickel, this tells you the proportion of cobalt and so on and so forth. There are 5 different elements, right. Now, if there are 5 different elements, there will always be regions of microstrains, right. So, microstrains are going to be different, the fluctuations in microstrains are large, right. So, this is one of the way of creating large fluctuations in microstrains. Right, very intuitively that makes sense, and because I am creating large fluctuations in microstrain, I measure a Young's modulus, right. So, these values of Young's modulus, if you look, and compare with, right. So, compare with the Young's modulus of either Fe. So, Young's modulus I am going to write Es, right. So, as they wrote here, that is not electric field, Es of Fe, Es of cobalt, Es of Cr, individually if you compare it with this, right. So, these are actually all greater than 200 gigapascals, right. So, here you are looking at Young's modulus which is quite small, right. So, this is much softer materials, right, and are so possibly because there are larger fluctuations in the microstrains in these high entropy alloys, because you are putting in a lot of components. So, it is possible that so there are lot, I mean, so it is very likely that there are many states, many microstates of different microstrains, and so the fluctuations in microstrains are also large. Okay. So, that is one of the examples I wanted to give you to in the mechanical domain, right. So, that is how I am getting lesser Young's modulus or larger compliance in the mechanical domain. Okay. So, now let us go back and so before starting Landau theory, let me actually define formally. So, again we are coming back from statistical mechanics. Back to thermodynamics. We started with thermo, right. We saw that thermodynamics is sort of a coarse grained approach, right, and then we said okay, so let us go back to so let us look at the microscopic origin of all these thermodynamic properties that I said. And now let us again coarse grain it and let us again come back to statistical mechanics, come back to thermodynamics, and then let us coarse grain things again. Coarse grain meaning I do not talk about micropolarizations anymore, I just talk about polarization, right. So, I just talk about an average polarization. I do not talk about microstrains anymore, I just talk about an average strain, right. So, in the system and so on and so forth, right. So, I give one what is called order parameter to the system. Right. Now, what is an order parameter? An order parameter is if I have two phases, phase 1 and phase 2, which are either structurally different or they are different in some way, and you will see that they are different in way of defining order parameter. You define what is called an order parameter, right. Phase 2 is typically the high temperature phase, phase 1 is typically the low temperature phase, right. As you increase the temperature, typically what happens? This is typical behavior is with temperature materials disorder. Okay. So, if I define something called an order parameter, I am going to say order parameter in phase 2 is equal to 0, some quantity, this is some physical quantity which in phase 2 is 0, whereas in phase 1 so this is some value, right. So, I am going to call it P or whatever, right. So, now if I have let us say I have a ferroelectric material, right. So, in a ferroelectric material, the order parameter in so I have a phase where I have polarizations which are all ordered, right, and then I have a this is a low temperature phase, and I have a high temperature phase where polarizations are all very disordered, the so called paraelectric phase, right. So, this is the high temperature phase. And in between, right, so I have a phase transition region where polarizations are trying to move from this configuration to this configuration, right. So, this is the phase transition region. So, what is a good order parameter here? A good order parameter is their polarization. This is the average polarization, but I am not going to talk about it in statistical mechanics terms, it is all thermodynamics, right. So, I am going to define P as the order parameter. P is non-zero in the low symmetry phase. This has a lower symmetry, right. The more disorder I make it, the higher symmetric I make it, right. So, this is lower symmetry, this is high symmetry. right. So, this is more disordered. This is more ordered. So, obviously, P in the low symmetry or the more ordered phase is non-zero, okay, and P in the high symmetry or more disordered phase is 0, right. So, this is a good choice of order parameter, because P is 0 in the high symmetry phase and P is non-zero in the low symmetry phase, right. So, typically I use this sort of a definition for any order parameter. Order parameter should be equal to 0 in a high symmetry phase and should not be equal to 0 in a low symmetry phase. Okay. There can be fluctuations, right. So, just like there were fluctuations in polarization, right. So, in my material there can be fluctuations in order parameter, that is okay. Microscopic domains is possible, but my order parameter is actually nothing but the averaged order parameter, right. So, if I am thinking, if I am still in the hangover of statistical mechanics, I am going to call it the average order parameter. So, the entire system is characterized by one order parameter, right, or if I am looking at a coupled problem by two order parameters, the order parameter in strain, the order parameter in polarization, right. So, the entire system is characterized in a particular domain, in an electrical domain, in a particular domain. Domain can be, by domain I mean an electrical domain or a mechanical domain or thermal domain, whatever it is, the problem, right, by an order parameter, right. So, I am not saying that, oh, my system, I am considering, this is the definition of what is called a homogeneous system. Although, if I zoom into the system, microscopically I will have different polarizations, but I am going to say this is a system with an average polarization 0, this is a system with an average polarization P. Okay. So, microscopically if I zoom in, there can be inhomogeneities, but I am going to coarse grain, that is what is called coarse grain. I do not see the microscopic picture, I magnify and I see the big picture. Big picture, this entire material or this entire system can be characterized by one order parameter or two order parameters, that is it, one in the mechanical domain, one in the electrical domain or something like that, right. So, I zoom out and then I look at the big picture, that is called coarse graining, right. So, I am back to thermodynamics hence. Okay. Now, let us consider a simple dielectric system, dielectric ferroelectric system, no mechanics here. Okay. So, only electric system. Okay. So, if there is only electric system, a good order parameter I said is polarization, right. Okay. Then if I look at a phase, a phase that is transitioning from so I have a tetragonal material that is transitioning from tetragonal T phase to a cubic phase, right. So, my C axis, right. So, the C parameter has changed from C1 to C2, right. If I plot C as a function of temperature, this is temperature, this is C, okay. C has gone from something like C1, C1 keeps increasing, and then so it has gone to some other value which is C2. So, this is C increases because of thermal expansion, and here C also increases because of thermal expansion, and here I have a phase transition. Okay. So, then I can always tilt this curve a bit such that I make sure I define, or so I am going to say that what is the order parameter here. So, I can always define that this line, right, as a function of temperature, this C2 of T is my order parameter, which means so I am going to say C minus C2 of T, that is my order parameter. C2 of T is this line. Okay. So, then in the high temperature phase, the C minus C2 of T, which is an OP order parameter, this is 0, right. In the low temperature phase, this has some value, and that value can increase, or so this is increasing more than this is increasing. So, that value will increase, right. So, this is the high temperature, sorry, this is the low temperature phase, this is the high temperature phase, right. My order parameter does not need to be unique. I can just define this structural quantity, which is the C lattice parameter minus C2, or C, meaning C can be in any phase, C2 is in phase 2, right, as a function of temperature, right. So, as a function of temperature, what is this curve doing, right. So, that is going to be my order parameter. This is a legitimate order parameter. Okay. So, I can this can be a definition of one of the order parameters, right. Or if I have a magnetic system with spins in all the directions, then so average magnetization, that is your order parameter in a magnetic system, right. So, you can have several order parameters, it's not necessarily a unique way of looking at things. Okay. So, for example, again if I go back to tetragonal to cubic phase, I am going from an average polarization which I have to an average polarization which is non-zero to an average polarization which is 0. So, polarization is an order parameter, but so also the C minus C2T is an order parameter. So, I can have multiple order parameters, it depends on what I want to see and what I want to define. Okay. Okay. So, in just a simple dielectric system, let us consider P to be my order parameter. Okay. Case in study here is P is the order parameter. Okay. Then now with this understanding of what an order parameter is, let us go and check out what Landau theory says. Now, Landau theory is just a phenomenological theory. There is phenomenological. Now, what is phenomenological theory? I mean, you do not need to put in certain parameters, you put in some equations and solve and get out some physics, right. So, you are not modeling based on physics, right. So, you just so you say that okay, I will just mathematically expand this and see what happens, and then I will extract quantities and then I get some physics at the end, right. So, the consequence of this is physics, but I am not putting in physics into my model to start with. I am just doing some empirical things to start with, empirical mathematical things to start with, and then I say that okay, rather than interpreting whatever I did here, I will interpret the results, right. So, that is phenomenology in some sense. Okay. So, this is a phenomenological theory where I start by writing my Landau free energy, this is called free energy, again this is thermodynamic theory, right. So, F is what is called the Landau free energy, right. Now, Landau free energy can be expressed as a function of F of order parameter. In this case, order parameter is P. If I have 2 order parameters, I will write both the order parameters. If I have 3 order parameters, I will write all the 3 order parameters, right. So, the free energy is a function of the order parameter. In what way I can actually expand it, right. So, I am going to say the free energy is equal to A naught plus A2 T square, sorry A2 P square plus A3 P4, or let me just write A4 P4 plus and so on and so forth. So, I am just going to polynomial expand of F in terms of P, and P is, I mean I can apply this to a ferroelectric system, I can apply this to a magnetic system or whatever it is, right. Now, why, I mean so there is some free energy of the system, and what this says is the free energy of the system is just determined by the order parameter of the system, right. Thermodynamically, I do not need to know all the microscopic details, I just need to know the order parameter of the system, and the free energy of the system is determined by the order parameter of the system. Now, what is the order parameter of the system? The so one order parameter dictates what is the total free energy that I need to concentrate on, right. So that is what Landau theory says, and what is any possible function, that is what is any possible f of p, right. F of p can be just Taylor expanded into some sort of a polynomial expansion, right. So that is what Landau does. So I take a free energy functional a free energy function f, there is the script f, and then I expand it in terms of a polynomial, right. So I do a polynomial expansion. Now, if you look carefully, there are only even terms in the even powers in the polynomial, and these even powers are p0, p2, p4 and so on and so forth, right. Why not odd powers? So essentially what I am saying is, if my system is characterized by either polarization up or polarization down, right, the energy should not change, right. So the energy, the free energy of the system and the free energy of the system should not depend exactly on what is the direction of polarization, rather it should just depend on the magnitude of my polarization, right. So the direction of polarization should not dictate, that is if this is not under the application of any electric field or whatever, right. So at when the system is left alone, that means I am not applying no electric field, nothing. Then so then I do not have to distinguish between the up polarization and down polarization have the same f. Okay. So that is a reasonable thing to start with, right. So there is no reason why so if it is up, right, so I am seeing it this way and the polarization is up. Now if I change my lab frame, right, so if I change my viewing axis and I view this from this side, then the same material will have a polarization which is down, right. So it is about the axis of axis by which you are looking at the material, and so whether it is up or down, the energy should not depend on the axis in which I am measuring it, right. So or the coordinate system in which I am measuring it. So the energy or the free energy of the system should not depend on the coordinate system I am measuring. As a result, I do not have any odd terms. So this is possible if I have only even terms, p0, p square, p4 and so on and so forth. Okay. So as a result, I have only even terms exist, no odd terms. Sorry. In the Landau potential expansion. Okay. So this is the free energy of the system. Now how does it look like when I do not apply any external stimulus, right. So when I do not apply any external stimulus, so this is one possible way in which this looks like. It is symmetric about the x axis, right, symmetric about the y axis. So this sort of a potential is symmetric about the y axis. It is not parabolic, it is, you also have higher powers, but this is symmetric about the y axis, right. So this is f as a function of p. Okay. So then so I do not need to consider all these Gibbs free energy, Helmholtz free energy, etc., which are dependent on so many variables. Landau potential just depends on one order parameter or one or two order parameters in the system that you consider, and so I am going to define it under so when I do nothing to the system, I am not forcing it with any forcing function, then Landau free energy is a symmetric function about the y axis. That means it is an even function. Okay. All right. Now, so let us start with f equal to f naught plus a2 p square plus a4 p4, right. So for starters, right, so we are going to look at what are called second order phase transitions. Right. So, where it is enough, right. So, again I said that this is a phenomenological theory where it is enough to go up to fourth, so for starters we can just go up to fourth order, right. So, p power 4, right. So, p power 4 term is enough. I do not need to consider the p power 6, p power 8 and other things. If I am looking at what are called first order phase transitions, I need to look at p power 6, p power 8 and so on and so forth, okay. P power 6 is, at least, right. Now, since it is phenomenological, I am just going to, so the free energy itself, right. So, there should be some sort of temperature dependence in free energy, right. And this temperature dependence comes in A2 in Landau theory. I am going to write A2 as some constant A2 tilde times T, and this T is what where all the magic is. T is actually T minus Tc by T. Okay, so let me just write it as T minus Tc for now, maybe we can normalize it later, right. Now, what is Tc? Tc is the temperature where there is a phase transition. Okay. So I am going to solve, I am going to look at what happens at the phase transition, right. So, there is a phase transition with respect to temperature, right. So, there is a phase transition, if I change the temperature, one phase, an ordered phase is transforming into a disordered phase. Ordered phase has some order parameter, in this case it is polarization, and it is transforming into a paraelectric phase or a disordered phase which has 0 polarization, right. And this happens at a particular temperature which I am calling it Tc for now, right. So, I am going to discuss what Tc is. Tc is a Curie temperature, for those of you who have heard of Curie temperature, okay. And so as a function of temperature, right. So, the polarization is decreasing, that is okay, the polarization, so we saw it in this picture that if I keep on increasing the temperature, the highly ordered phase comes down to a disordered phase. So, the polarization keeps on decreasing, okay. So, that is fine. But so there should be some form of temperature dependence also to F, and the temperature dependence I am going to this is a phenomenological theory where Landau sort of said that the temperature dependence goes into the p square term, okay. So, in the p square term I am just going to write p square as A2 times T, where small t is just T minus Tc. How close are you to the transition temperature, that is what this tells me, okay. Okay. Now, what should happen at equilibrium? Now, at equilibrium, so the first derivatives of free energies are zeros. So, dou f by dou p equal to 0, and that means that so 2 p A2 t plus 4 A4 t, right. So, this goes to 0, so this is the first term and this is the second term, p cube equal to 0, right. So, how many solutions does this have? This has 2 solutions, solutions. This is just a quadratic equation for equation 1, solutions for equation 1 are as follows, which is A p equal to 0 is a solution, or p equal to plus or minus square root of minus 2 A2 tilde t divided by 4 A4, okay. Now, I am doing Landau theory where there are certain constraints that I impose. I am just expanding up to, right, I am just expanding up to fourth p power 4, right. Then b, I am going to say that A4 is greater than 0, right. So, this is a constraint. So, if I am just expanding up to p power 4, mathematically for this to have any solutions I need A4 to be greater than 0, okay. So, it's a that makes this some sort of a bounded problem. I will not have any mathematical discrepancies. If A4 is less than 0, then I have to expand up to A6, right. So, the last coefficient should be greater than 0, right. So, that's how much I expand up to, okay. Alright. So, if that is the case, then so we said that we have so p equal to 0 is a solution, p equal to plus or minus square root of minus 2 A2 tilde t divided by what was it, 4 A4. All right. So, when t is greater than 0, right. So, again so A2 is A2 tilde t, right. So, remember this, where t is just t minus T c, right. So, A2 can have positive value, A2 can have negative value. A2 is positive if t is greater than 0, A2 is negative if t is less than 0, which means A2 tilde is a constant which I always make it greater than 0. Okay. So, this is something else. Okay. Now, A2 tilde, so A2 tilde is always greater than 0. So, when t is greater than 0, my polarization has only one solution, right. So, t greater than 0, I have only one solution, p equal to 0 is the equilibrium state, right. When t less than 0, I have three solutions, which is p equal to 0, p equal to plus or minus square root of minus 2 A2 t by 4 A4. Okay. Now, t is less than 0 means temperature is less than Tc, right. Temperature is, this is the low temperature phase, and this is the high temperature phase, and of course, at high temperature phase we said P is equal to 0, right. So, this is t greater than Tc. Okay. So, now if I plot the entire f as a function of P, right, at different temperatures, right. At relatively higher temperatures I just have one solution. So, wherever dou f by dou p goes to 0, that is my stable solution, that is my this is the solution. Okay. So, then when at much lower temperatures I have three solutions, and it turns out that you can see p equal to 0 in this case will be an unstable solution, or if you calculate dou 2 f by dou p square, that will be less than 0. That gives constraints for stability, right. So, not just equilibrium is dou f by dou p equal to 0, stability is dou square f by dou p square is also greater than 0, right. But p not equal to 0, these are the stable solutions, right. So, that is dou 2 f by dou p square is greater than 0. Okay. So, at much lower temperatures I have something which goes like this, correct. So, this is as a function of I am increasing temperature, right. So, this is T1 is low, T2 is high. Okay. So, so p equal to 0. Okay. So, let me symmetrize this. So, this is not my x axis, rather this is my x axis. Okay. So, p equal to 0 is a solution, but it is an unstable solution. If I leave the system here, the system will either fall down here or fall down here, right. So, it will just slide down to one of the two wells. Okay. Whereas, if I leave the system here, the system stays there, right. So, these sort of potentials are what are called double well potentials, which means my ferroelectric or my magnet can either be in the up state, which corresponds to one well, which corresponds to this well, right. So, it can be in the up state, which corresponds to this well, or it can be in the down state, which means polarization is negative, which corresponds to this well, right. So, the system can be here or the system can be here, right. So, that is what this means, I have a double well potential, and in between so this thing, right. So, here if my system is here, my system cannot have 0 polarization. If it has 0 polarization, a little bit of perturbation will just take it either here or here, right. So, this is an unstable solution, right. Whereas, in the high temperature phase, p equal to 0 is the stable solution, I do not have any double wells or anything, this is just a single well potential, no double wells. Okay. Okay, fine. So, with that if I actually start, but what is the value of this p, right. So, the value of this p is plus or minus square root of minus 2 A2 tilde t, that is a positive number, divided by 4 A4, right. Now, as I keep on increasing the temperature, right, so towards Tc, right. So, I am at T less than Tc, right, but as I keep on, as temperature increases towards Tc, right, the value of T, the magnitude of t starts to decrease, right, or t minus T c, the magnitude of that is decreasing, or okay. So, t is a negative number. So, let us put it this way, this is easier to understand. So, minus t will start decreasing, minus t will start decreasing. Okay. So, minus t is a positive number. So, if I just plot this, right. So, if I just look at what p is as a function of temperature, as a function of t, p will start somewhere and then it will start to decrease like this, right. So, it will start to decrease as a root t dependence, right. So, that is what you have for p, and then you have, okay. So, let me plot it here in the next page. So, I have, if I am just plotting p as a function of temperature, p is reducing as a function of temperature, right. So, with you know, close enough to the phase transition, it is reducing as square root t, right. But I have another solution, right. So, this is solution 1 which is doing this. I have another solution which is also exactly doing that, right. So, it is going towards 0 from something which is non-zero, right. How does the, you know, so the potential, right. So, if I just look at the double well potential F, you know, so I have a value of polarization which is here at lower temperatures, right. Now, this value of polarization will start going towards 0, the equilibrium value of polarization will start going towards 0. So, at higher temperature it is this, right. So, slightly higher temperatures. And even at higher temperatures it is going to be this, right. So, there is this, there is this. So, these are the polarization trajectories that I am plotting here, right. So, these are the same polarization, this is polarization, right. So, the values on the x axis here climb up to the y axis here, right, and eventually, you know, so there is going to be a point where polarization goes to 0, right, and you know, so after that, you know, so the only solution I have is p equal to 0, right. So, this is the point where I have a phase transition. That is the point where t, small t equal to 0 or capital T equal to T c. Okay. So, that is my phase transition point. Okay. All right. So, let us, sorry, let me just draw this again. Okay. So, let us end this class here, right. So, let us begin in the next class from you know, so the description of what is, so here we have actually seen what is happening to the order parameter while there is a phase transition. In this potential, the way we have defined it, you know, this order parameter actually goes to 0 with a square root t dependence, right. So, so we will look at you know, what happens to susceptibility and other things in the next class. Okay. So we will continue upon just this very simple form of Landau theory. Okay. All right. So, I will see you in the next class again. Thank you.